In this example, we have a helicopter that's rising vertically at a uniform velocity of 14.7 meters per second. When it reaches a height of 196 meters from the ground, a Rottweiler is projected vertically out of the helicopter, horizontally out of the helicopter with a velocity of 8.5 meters per second. We're going to figure out where the dog safely reaches the ground, how long it takes for the dog to actually make contact, and with what velocity it hits the ground. And of course, don't worry, the dog is completely safe. So let's start off by, as always, trying to draw a picture if we can. So if this is our ground, we have our helicopter up here. This is 196 meters high. And then our dog is going for a ride this way at 8.5 meters per second. And let's not forget um, that we still have, the helicopter doesn't stop, so it is rising continuously. So there is a vertical component to velocity as well, 14.7 meters per second. So let's take a look at our vertical and horizontal components, and then we can figure out how we're going to tackle this problem. So vertically, we know that our v1y, our initial velocity in the vertical direction, is 14.7 meters per second. And we're going to say again that up is positive, down is negative, left is negative, right is positive, or forward is positive, backwards is negative. Our displacement, so the distance the net distance that the dog is going to end up traveling, since it's going down, right? We're going to say negative 196 meters, and so that's in the down direction, which is why that's negative. And then our acceleration due to gravity is always constant, negative 9.8 meters per second squared. Again, negative because it's going down. In terms of our horizontal components, all we have is our velocity, v1x, 8.5 meters per second, and that's positive because it's in what we've defined as the forward direction, and that's relative to my picture. So if I had drawn it the other way, you could say it's negative. So given the previous information, we're again going to calculate our horizontal displacements relative to the time it takes. So because time is going to be the only thing that's the same between the vertical and the horizontal components. So step one is going to be to calculate the amount of time it takes. So we're going to use our equation, the displacement in the y direction is equal to the velocity in the y direction times time, plus 1 over 2 AT squared. So plug in everything we know, 196 meters. That's negative because it's going down. Positive 14.7 meters per second times time, plus a half of negative 9.8 meters per second squared times t squared. I'm going to rewrite this so that it looks like ax squared plus bx plus c. I'm just going to get rid of my units to make it a little bit easier. And of course, instead of x, we have t. So it's not ax squared plus bx plus c, it's at squared plus bt plus c. So of course, that's a quadratic. We can use our quadratic formula, which will look like this. T equals negative b, which is 14.7, plus or minus the square root of 14.7 squared, so that's b squared, minus 4ac, which is minus 4 times negative 4.9 times 196, all over 2a, which is 2 times negative 4.9. Once you go ahead and plug that in, solve for that, you're going to get two answers. We end up with t equals 8 or negative 5. Now, of course, negative 5 isn't good. We don't have negative time, so it's got to be positive 8. So that's 8 seconds. It takes 8 seconds for this dog to reach the ground after flying from the helicopter. So therefore, and you can give a statement, 8 seconds. Next up, we're looking for the distance it traveled, so where it hits the ground. We know it hits the ground 196 meters from the helicopter vertically, but how about horizontally? So where from the helicopter horizontally is this dog located? Well, we can say our change in displacement in the x direction is equal to our x velocity times time. This is all stuff we know. So the x velocity is given in the question, 8.5 meters per second. It's positive because we've defined that forward direction to be positive, times 8 seconds. And that leaves us with 68 meters. So you have a therefore statement. Therefore, the dog lands 68 meters in front of the helicopter, for example. Lastly, we're looking for the velocity at which the dog is going to impact the ground with. So we should draw the picture here just to give us a little bit more information. But before we do that, we need to know what the values are that we're going to be using. So of course, if our dog is leaving the helicopter, it's going to have a horizontal component, which we know that's 8.5 meters per second. But it's also going to have a vertical component. And that vertical component is going to depend on the initial vertical velocity and as well as the acceleration. So we don't actually know this yet. We need to do a little bit of math to calculate that. After we have that, we can find the resultant vector. And also we can look for this angle in here. So this is actually going to be v2y, which we can solve for. If you recall that the acceleration is equal to the change in velocity over time, we can rearrange that to say that v2y is equal to v1y plus ayt. And this is going to give us the vertical component of our acceleration and of our final acceleration more specifically. So I'm just going to plug in everything I know. So I know the initial vertical component of acceleration because that's given to me as the helicopter is rising, right? So when we're starting off, the dog and the helicopter have the same initial velocity, and that's going to be 14.7 meters per second. Now here's where it changes because the dog is going to have a negative acceleration due to gravity, negative 9.8 meters per second squared, and we know how long this whole process takes, 8 seconds. So when we solve for all of this, we end up with negative 63.7 meters per second. This gives us 63.7 meters per second down. Okay, because again, we've defined negative to be down. So that makes sense because if we look at our picture, of course, that resultant vector is going down. So that leaves us here with 63.7 meters per second. Now we have a right triangle, so we can solve for this V2 component, which is what we have here. This is our V2, our final velocity. So we can say V2 is equal to the square root of the x component squared plus the y component squared. So that's 8.5 squared plus 63.7 squared. When that's all said and done, we have our V2, which is equal to 64.3 meters per second. Now at this point, it's not a vector value yet because there's no direction to it, right? This is just a scalar value. So we can figure out the angle by using our tan ratio. So our angle theta is tan negative 1 of 63.7 over 8.5, which gives us a value of 82 degrees. So our actual vector value would be 63 or 64.3, 82 degrees below the horizontal. So we would say that V2 as a vector is 64.3 meters per second, 82 degrees below horizontal. And that's the velocity at which the dog impacts the ground with. Now, this is a superhuman dog or a super dog, so it will survive this fall.